Okay, now this is the online class of mathematical physics for March 19, March 19. And today we're going to talk about the other perpendicular components of the speed projectile. I hope you still remember that last week we already solved the horizontal component of velocity of a projectile motion, of course, with air resistance. And now let's move on to the other the other components, that which is the perpendicular component Vy. And as you have remembered, the equation of motion, the differential equation is dvy dt plus k over m times Vy. Up to these two terms, it is totally identical to the equation of motion for Vx. However, for the vertical component, there is a gravitational force. Therefore, there is a minus g on the right-hand side. Okay, so this minus g is independent of the function we are going to solve, Vy. Okay, therefore, this v minus g actually changed the whole character of the solution. And this is one of the we call linear first order ordinary differential equation. Its first order is that it is first order is obvious. However, here we add a new name for this kind of equation, linear. Okay, we will see that from first order on, actually we are only able to solve linear equation completely. So therefore, this linear name is very, very important. It's very important. Okay, so the most general linear first order ODE could be written in this way: dy over dx plus a function of x times y. So you can see the correspondence between this general form and the form, the perpendicular components Vy we have talked about. And this equal to Qx. So this Qx corresponds to the minus g on the right-hand side of the original equation. So this is the most general form, almost the most general form of the linear first order ordinary equation. The key character is there is only one power of derivative of first order and one power of y and a known function of q. There is no y square or dy dx square or cube. If there is a y square, then it is nonlinear. Remember, and the interesting thing is that in the physical world, almost all the ordinary differential equations you are going to encounter are linear. So that's why we are going to take advantage of this linearity of the equation to have very, very simple answer to the question. Okay, so let me introduce some terminology which will be very, very useful later. If we look at this equation, linear order, first order ODE, if we get rid of Qx, this Qx is sometimes called source term. Why it is called source term will become clear next week when we talk about this linear ODE for the second order. And if we get rid of this source term, it is called a homogeneous version. That is, without this Qx, dy dx plus px times y is equal to 0. Then we'll call it the homogeneous version. Okay, And with this Qx, it is called inhomogeneous equation. Okay, then the solution, we will show you later very soon, the solution for the inhomogeneous equation is highly related to the homogeneous version. Okay, now let's apply these let's apply this terminology to the equation we are going to solve. For the inhomogeneous decay equation, for the equation for Vy, maybe we can call it inhomogeneous decay equation because it will become clear later. For this inhomogeneous decay equation we are solving, Qx is equal to minus G. Okay, and without Qx, the homogeneous version, remember, is identical to the decay equation. Without this minus G, it simply becomes dvy dt plus k over m times Vy equal to 0. Okay, and this you can very easily identify it with the decay equation or with the equation for Vx we have talked about last week. Therefore, one more time, the homogeneous version of this equation we are going to solve is actually the decay equation. That's why we can use this terminology we call inhomogeneous decay equation. Okay, so this terminology will be very important, and we are going to solve this so-called inhomogeneous decay equation. This time, we will now move on to the number function. We will stick with Vy when we solve this equation. Remember, this is also the equation satisfied by a free-falling object with air resistance. That's the reason is that the horizontal motion and the vertical motion are independent with each other. Therefore, the same equation will apply to all the projectile motion with or without horizontal motion. So the equation is actually the same as a free-falling. When we talk about free-falling objects, we can think about like a parachute or a ball falling inside a liquid. For an equation this simple, you can immediately guess a solution. We call it the equal speed solution. Remember that if Vy is a constant, that's why we call it equal speed. If Vy is a constant, then dvy dt is just equal to 0. So if dvy dt is equal to 0, then minus g minus k over m Vy is also equal to 0 according to the equation of motion. Therefore, Vy would be equal to minus mg over k. It is a constant, and if you plug in this solution into the equation, you will see very soon this solution does satisfy this equation. Okay, so this is we immediately can guess a solution to the equation, the inhomogeneous decay equation. However, so this is apparently one of the solutions of the inhomogeneous decay equation, but it is unlikely to satisfy most initial conditions. And we know that in all the free fall, or in almost all the free fall motion with air resistance, the speed will change. Therefore, this equal speed is, even though it is one of the solutions, but it could not be the most general solution we are going to use. Okay, so but this equal speed solution will come back at the end of our work. So remember, there is something called equal speed solution here. Okay, just as before, we will have method 0, method 1, and method 2. Method 0 is to solve the equation in the most intuitive way. It's not difficult, but I will skip this part. You can just take a look when you study the material. The simplest idea, the idea is actually very, very simple. you can actually define a new function we call capital V, which is the Vy plus mg over k. We did this because if we do this substitution, then the right-hand side is just equal to k over m times capital V. While the left-hand side, dvy dt, is equal to d capital V dt, because the difference between the two functions is just a constant. Okay, so their derivatives are identical. Therefore, by this substitution, in which I mean I use a same function capital Vt, we can rewrite the original equation into a form which is just the decay equation. Okay, so this is very intuitive. So if with this, but we know how to solve the decay equation. Then, so V is known, so the V is known as before, and then you can go back from here to Vyt very easily just by adding the constant you are supposed to add. Okay, therefore, this is the solution has come to this. Okay, so yeah, so here is a diagram of how the function look like, but we'll skip this part also because we are going to use a more general and more useful method to solve this equation very soon. Okay, so now there is also a method 1. Method 1 we are going to skip also, but let me tell you what is method 1. Method 1 is to recognize that the inhomogeneous equation is actually a separable equation. It's easy to see because the right-hand side consists of only a function of Vy and there's no t. Okay, therefore it's separable. Therefore I can pull the right-hand side to the left-hand side and dt to the right-hand side and then do integration. So it's the same method we have introduced last week. Okay, so this is method 1 refers to the method we used last week. However, I'm not going to sit down and finish the calculus, but we are going to introduce another new method we call integrating factor. This integrating factor is is invented by Leibniz in around about 400 years ago. Okay, you remember Leibniz is one of the mathematicians who invented calculus, derivative differentiation with Newton. Okay, so this method actually is very old and historic, and it's very, very beautiful. Okay, so now method 2. In order to make our mathematical notation simpler, let's drop the subscript y for simplicity. Okay, but remember when I talk about v, actually it is vy. So the equation we are going to solve, dv dt plus k over mv is equal to minus g. What we are going to do is to multiply both sides by exponential k over m times t. This thing is called integrating factor. Later, we will give you a general recipe to create, to write down the integrating factor. But here, we just introduce the integrating factor directly into our calculation. So, multiply both sides by exponential k over m times t, exponential k over times t here again. Why we did this is then, after multiplying the equation by this integrating factor, the left-hand side are actually the derivative of a function. It's easy to see. The function is exponential k over m times t, that is integrating factor, times v. You can check by chain rule, making this first derivative, then by chain rule, you would make a derivative of the first term. It will give you this times v without derivation. And then the derivative will act on v and give you dv over dt without making the differentiation of the first term. So exponential k over m times t will stay here. Therefore, it's easy to see that this term is here, this term is here. Add them together gives you a total derivative of exponential k over m times t over v. This is equal to the right-hand side minus g exponential k over m times t, which is a function of time. Okay, so we now know that this function, the derivative of this function is this function. Therefore, it is easy to integrate both sides to get exponential k over m times t times v is equal to the right-hand side g exponential k over m times t integrated over dt. But remember, whenever we did the integration, we can always add a constant in front of it, because when you make the derivative of the whole equation, this c will disappear and give you exactly the same equation we start with. Okay, and this integration is easy to make. The answer is m over k times exponential k over m times t. We are almost done, because here we have an ordinary equation. V will appear right away if you move this exponential factor to the right-hand side. To the right-hand side, it makes c times exponential minus k over m times t. And the second term, this exponential factor simply cancels out. It becomes minus mg over k. So this is the solution we arrive at. And remember, here is a c. Therefore, the constant, the unspecified constant will appear automatically. Remember, this unspecified constant is very important for our calculation. It will fit the initial condition. Okay, so with this unspecified constant, we again arrive at an infinite number of solutions, but the constant can be used to fit the initial condition, and finally we'll get just one solution. So this is the so-called integrating factor method. It's very beautiful, and the solution can be derived and calculated step by step systematically. Okay, so if we put in the initial condition, you will see that Vy is equal to Vy0, that's the initial condition, plus mg over k times exponential minus k over m times t minus mg over k. So let's take a look at how the function will change over t. When t becomes larger and larger, then this term becomes smaller and smaller. Therefore, the difference between Vy and minus mg over k becomes smaller. So here, I should probably put this Vy as minus Vy, because this Vy actually is downwards, and therefore it is. If you want the vertical speed, then you probably need to make a negative. Okay, so with negative here and positive here, then when this first term becomes smaller and smaller, then the speed will become larger and larger like this. And you will see very clearly when this term, when t goes to infinity, then it becomes 0. That means the speed of the motion will get close and closer and closer and close, almost approaching this value of minus mg over k. So now we see what this minus mg over k, this constant means. This constant is the final constant speed, the vertical motion with air resistance will approach. In high school physics, we usually call it terminal speed, 终端速度. Okay, so when you throw a thing downwards, then it will approach. For example, if you have a parachute or a ball inside a liquid, initially the speed will will increase. However, after a long time, then it will approach a constant, as this function shows you. Okay. So this is the solution, and you can see that the integrating factor is actually very, very useful. Now, in the above derivation, I use the specific example of this vertical speed. However, this integrating factor can be generalized to all the first order ODE. dy dx plus pxy equal to qx. Okay, so in the following presentation, I will list I will list the corresponding the corresponding steps in the earlier derivation, so that you can see them in contrast to each other. Okay, so now let's apply this integrating factor to the general equation. The idea is again to multiply the left-hand side and the right-hand side by a function integrating factor. Now I will call it alpha x. This alpha x, of course, corresponds to the exponential k over m times t, which we multiply both sides in the earlier derivation. Alpha x. Now, I multiply both sides by alpha x, and we expect the left-hand side to become the derivative of a function. This function is alpha y. Therefore, we multiply by the left-hand side by alpha. It will become something like this. And we expect it to become equal to alpha y, the reverse derivative of alpha y. So it is easy to see that in order for this equation to be satisfied, this alpha must satisfy d alpha dx minus px times alpha equal to 0. So that means this factor must be equal to d alpha dx. So that I think that's not very difficult to see. If you use the chain rule to make this derivative, then you got the first term, and the second term should have been d alpha dx times y. Then d alpha dx, if you want this equation to be satisfied, then d alpha dx must be equal to this p alpha. So by chain rule, the condition for this alpha to be the integrating factor, it is d alpha dx minus px alpha equal to 0. Then this equation is easily solvable, which is because it is a separable ordinary differential equation, which we already know how to solve. Okay, the answer is alpha equal to exponential px. Let me review how it is done. I think I have I have it here. So with this condition, we can move this px alpha to the right hand side, and move alpha to the left hand side, and dx to the right hand side, and then integrate the whole thing by integration. Then you will get alpha 1 over alpha d alpha equal to the px times dx integration plus c prime. And this integration is easy. It's log alpha, and it is equal to the integration of px over dx plus, again, when you do the integration, you can always add a constant c prime. The result will still be satisfied. Therefore, take the exponential of both sides. It becomes alpha equal to exponential integration px times dx. So that's how we get the integrating factor. Okay, integrating factor. You can check actually this is true with the earlier derivation. This exponential k over m times t. Remember, p is k over m. Therefore, this alpha x, if applied to the earlier derivation, you will have exponential k over m integration, then it will be k over m times t with exponential. Okay, so you can check this general formula actually apply to the original derivation. Okay, with alpha, with the integrating factor solved, we can just apply it into the equation we are going to solve. The left-hand side, again, this is the equation we are going to solve, and multiply both sides with the integrating factor. The right-hand side becomes alpha q. And then the left-hand side is equal to the derivative of alpha y. That's the condition. And it's equal to alpha times q. And then we can make integration of both sides, and again add the constant c to our result. Then alpha y will be equal to alpha q integration plus c. Then move the alpha to the right hand side. Y has been solved. Y equal to c over alpha plus 1 over alpha. Remember, this alpha in the denominator actually comes from here. Okay, when you move the alpha to the right hand side, you got c over alpha plus 1 over alpha times the integration of alpha q. It's done. It's very abstract. But the formula is there. So whenever you have an equation like this linear ordinary equation, you can simply put in every data and every factor, and then the solution is there. And this solution is general. Remember, here we have a constant c for us to fit the initial condition. Okay, so everything is automatic and systematic. So that's the beauty of this integrating factor method, because you don't need to do anything. You only need to remember the formula, or of course, if you want to derive, make the derivation on your own, you will be very satisfied. However, you can also just remember the formula and put in all the factor, and the answer is right there. Okay, now we can compare the general method and the specific example we have already solved the equation for Vy. I don't need to derive to explain it here. You can simply compare each other and see the answer is true. Okay. Just remember here, the alpha is exponential, the k over m times t. Okay, and then therefore this alpha in the denominator will become exponential minus k over m times t. It's an exponentially decreasing function. And the second term is actually a constant minus mg over k. Okay, so that's the end of presentation of integrating factor. Okay, at least one in the midterm exam, and at least one problem will be about this integrating factor. I'm not sure if you will need to use it in the future study of physics. Okay, I didn't use this method at all. However, it's so beautiful. It's so beautiful method. So I hope you will enjoy studying it. Okay. But however, even though the integrating factor may not be useful in your future study, however, if you look at the solution, there is one very, very interesting thing that will have long-term consequences. When I say long-term consequences, it means the result could be applied to more general cases. If you take a closer look and concentrate your mind on the solution we have finally got here, okay, C exponential times exponential minus k over m times t minus mg over k. Actually, this solution contains two terms, and these two terms are actually familiar terms we have already discussed. If you take a closer look, the first term are actually the solution of the homogeneous version, right? Remember I told you that the homogeneous version of the inhomogeneous decay equation is just a decay equation. The solution of decay equation is exponential decreasing function, just like this. Okay, I don't need to go back to the earlier transparency, to the earlier PowerPoint transparency. You can see clearly this is the solution of the homogeneous version decay equation. How about the other term? I got a decay equation here. How about the other term? Mg over k, if you still remember what I said earlier, we call it equal speed solution, right? This is a solution of the inhomogeneous decay equation, okay? And but however, at that time I told you that this solution is unable. This equal speed solution is unable to satisfy. Is unlikely to satisfy all the initial condition. But here, if we add in a solution for decay equation, then we got a C here. Therefore, with this addition, then the result could have a chance to satisfy all the initial condition. Okay, so that's the beauty of this thing. We got a special condition, special solution, and then a solution for the homogeneous version, and with the C to satisfy initial condition. Okay, so this observation told us that a very fascinating fact: solution of linear inhomogeneous ODE equals one solution of the inhomogeneous ODE, which is this, plus the solution of the homogeneous version. Okay, yeah, so therefore, if you can guess, this not only applies to Vy, it also applies to all the general cases when we use integrating factor to solve it. Remember, when we solve this general case, general linear ordinary equation, ODE, then the condition for integrating factor is like this. And the solution of alpha is like this. But if you are observe carefully, this condition is actually the homogeneous version with minus p replacing p. Okay, that's the difference between the sign here, but that means the solution of the homogeneous equation is exponential minus p integration, and it is equal to 1 over alpha. It is equal to 1 over alpha. So that means the integrating factor has a very special property. It is equal to the inverse of the solution of the homogeneous version. Therefore, when we look at the solution we have written down earlier, y equal to c over alpha x, the first term, are actually the solution of a homogeneous ODE. That's called y1 here, okay? So the reason is that the integrating factor alpha is equal to the inverse of the solution of a homogeneous version. Okay, so that's why we call it y1. And then y2, this very complicated form is one of the solution of the inhomogeneous ODE. If you take, because it's easy, because C could take any value. So if I put this C equal to 0, then only the second term will be left. However, I can choose C equal to 0, then the second term still satisfy the inhomogeneous equation. You can just plug in to check it is true. Here I call it y2. y2 is a solution, one of the solutions of the inhomogeneous ODE. Okay, so again, you can see that this is the general property of all the linear ordinary equation, such that the solution of an inhomogeneous version is equal to the solution of the homogeneous version plus one of the solution of the inhomogeneous equation. Okay, yeah, so this is very, 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 very general. Huh? Here I prove it to the ordinary. There is another way to prove it, which could be applied to linear equation to order. Here, I say that the solution y of a linear inhomogeneous ODE is equal to one solution, let's call it y2 of the inhomogeneous ODE, plus the solution y1 of the homogeneous ODE. The reason is simple. If you take the difference between the two solutions I mentioned here, y is a general solution, y2 is a specific solution, then if you take a difference between them, y minus y2, then you will see that the difference is actually equals a solution of the homogeneous ODE. It's simple. Y satisfies inhomogeneous version. Y2 also satisfies the inhomogeneous version. You have to take the difference between the two equations, then the right-hand side will cancel right away and equal to 0. The left-hand side, dyx minus dy2 dx, could be written as dy minus y2 over dx. The second term will be easily rewritten as px times y minus y2. The right-hand side, as I have mentioned earlier, q minus q just vanish. Okay, therefore y minus y2 satisfy a homogeneous version of the equation. So that's why we can call it y1, and therefore y is equal to y1 plus y2. Okay, therefore remember, this y1 is very, very important because y1 is the solution of the homogeneous version. And remember that we always need the solution to provide enough freedom to accommodate the initial condition. Mostly the freedom takes the form of unspecified constants. Here, for the solution we have got, the unspecified constant comes from y1, the homogeneous solution. Okay, so if we put in a proper initial condition, the constant will be specified, and there is only one solution. Okay, so that's almost all I have to say today for this section. But let me summarize by a very, very clear diagram. For first order ODE, the most general form could be written as dy dx equal to a function of y, x. There is no general solution to this general form. However, if the f is simplified could be simplified to px over qy, we'll call it separable. And then, as I showed you earlier, you can just pull the q to the right hand side, dx to the right hand side, and take integration. Okay, and the solution will be, we will get the solution like this. There's another simplification that will make the solution available. If this fyx could be written in this form, that is dy dx plus p times y equal to q. This, we usually call it linear first order ordinary equation. And then, as I have shown in the past hour, we can use the integrating factor alpha to make the left-hand side into a derivative of alpha y. And then you can again take an integration so that the solution will be got. Okay, we'll get the solution. Okay, so that's a general case, what we can say about the first order ordinary differential equation. And if you remember, both methods can only apply to first order ODE because they depends on, depends on the left hand side is dy dx, and then you can pull the vectors over the other. And these methods can only apply to first order ODE. So therefore, that's why these methods probably will not be very, very useful, because in physics, most of the differential equations are second order. So these two methods could not be applied to your future study most of the time. However, because the ordinary first order ODE are the simplest ODE, so it's very, very, we still provide this calculation as the first step into the differential equation. However, there is one method that could be applied. That is, when we take a look at the linear first order equation, then we see that it is a non-inhomogeneous ODE. However, it could have a homogeneous version, and we have already proved that for inhomogeneous equation, the ODE equation, the solution equals one solution of the inhomogeneous plus once the solution of homogeneous. This calculation, this conclusion actually applies to linear ODE to all orders, And in the next hour, I will start to talk about simple harmonic motion, and you will see this result, this conclusion could be applied to the case of simple harmonic motion. Okay, so here is about the end of our first section of the teaching. Let's take a break.